since we skipped a lecture. We're going to sort of look at different aspects of this boundary term. So today I'm going to be focusing more on the boundary term as it is, but I want to kind of use that to lead into a discussion more generally about non-perturbative aspects in gravity, because quite often when we're using gravity, we think of things as either being exact solutions like black holes or cosmology. So that is non-perturbative in a sense, but I guess we don't feel it because they're out there in the universe and there's so much symmetry in the metric that it is essentially integrable. Or we're doing perturbative gravity, which I will discuss briefly next week, which is where we're thinking about something that's close to an exact solution. So a good example of that is perturbations in cosmology. So we kind of do cosmological perturbation theory to explore how galaxies and structure in the universe forms. We also do perturbation theory often when we're thinking about gravitational waves. But as David was very keen to point out to me in a discussion, actually, gravitational waves don't need to be perturbative. So I don't know whether we'll either have time to do that in a lecture or a tutorial or some extra discussion session, I don't know. But there's also another example where gravity sort of has this non-perturbative aspect. And these are the sort of two examples I want to think of today. So one is going to be extremely formal. The first one I'm going to do is I'm going to look at the Euclidean action of the Schwarzschild solution. So this is sort of from the perspective of doing fake quantum gravity, if you like, in the sense of we're trying to do quantum gravity. We accept we don't know what the theory of quantum gravity is, but we'll say that as long as we don't hit the Planck scale, we can approximate things using our sort of standard ideas from quantum field theory, and we'll sort of include gravity so long as it never takes us to one of, to the Planck scale, to one of these 6 scales. And also, I think with the knowledge that there's something we're doing that's sort of slightly cheeky. So I think, for example, the Schwarzschild black hole has a temperature proportional to 1/m, okay? So that means if it radiates and loses mass, it gets hotter. That's peculiar. It's got negative specific heat. So that suggests it's really not in thermal equilibrium, because if it sits there and radiates, it loses mass, it gets hotter. So it's and then it has a runaway instability, which is black hole evaporation. So even though we use the Euclidean method to derive the temperature of the black hole, we are being a little bit sneaky and a bit cheeky, because this notion of periodic Euclidean time corresponding to temperature is something that we do in thermal equilibrium or approximate equilibrium. And of course, the black hole isn't, at least not an isolated vacuum black hole. So I believe David has a neat tutorial about black holes in anti de Sitter, where things are more interesting. So if I sketch the RT part of the Euclidean Schwarzschild geometry, I get what gets called a black hole cigar. So here, this is our Schwarzschild manifold. Near r equals 2gm, the space-time is smooth it closes off. It's like the origin of r squared in polar coordinates. So we have locally just some little piece of flat space. But as we go out and ask what is the circumference of the circles of r equals constant, the circumference starts off growing because, of course, GTT as we move away from r equals 2gm, our circumference grows like the square root of r minus 2gm. But then as we get to very large r, it approaches a constant. So it approaches 2 pi beta, the length of those tau circles. And so if we wanted to embed that, sort of represent that space-time as an embedding, this is what it would look like. So for Schwarzschild, the Einstein-Hilbert action is identically 0 because it's got no Ricci curvature. Mm-hmm.
In this cigar picture, does the R coordinate only go down to 2gm? It doesn't go below?
That's right. It just goes to 2gm in this picture because the space-time smoothly closes off there. Right. So if you remember when I was writing down the Euclidean solution, if we just analytically continued, if we tried to think of r being less than 2gm, then the signature would change. We'd have minus, minus, plus, plus, which is quite, that's a dramatically different space-time. So that is 0 for the Schwarzschild solution. But what about a Gibbons-Hawking term? So let's now think about this extra term that we've argued should be present in the gravitational action. So I'm going to truncate my space-time here at some large r, okay? So I'm going to truncate it at capital R, and we're going to look at the Gibbons-Hawking boundary term for that boundary of the manifold. So this is our boundary metric. And notice that R here, from the boundaries perspective, this is just some constant sitting in this lower dimensional metric. And the only sort of non-trivial dependence is hiding in the d omega piece. So this geometry, this submanifold, has curvature because the S2 is curved. It's a constant positive curvature space. But it doesn't have curvature because of the capital R in an intrinsic sense, because R is just a constant. However, considered now as a submanifold living within the higher dimensional Euclidean Schwarzschild, it does have extrinsic curvature, which does depend on R. So the normal, if I look at the surface, the normal is dr, which is also proportional to d by dr in this Euclidean space. So I simply normalize my n. So this is what the normal is. And if I wanted to think because I'm going to need to take a derivative or think about how n changes, then if I want to normalize this field, to make it unit, I just multiply by root 1 minus 2gm on R. So the extrinsic curvature, which I need to calculate, so K is the divergence of n. The trace of the extrinsic curvature is just the divergence of n in this gauge. And so we know that we have this useful formula for divergences, which sort of has a 1 over root g partial derivative of root g times your vector. So here, my root g, well, root g is, of course, referring to the parent manifold. And so root g is just r squared sine theta. And, of course, n just has an r component. So I get 1 over r squared nr prime. And, of course, nr is just root of 1 minus 2gm on r. So this is 2 over r root 1 minus 2gm on r. This is, of course, valuated at r equals r. So this is what I get for my extrinsic curvature, which I have to evaluate at the boundary. So I simply replace the little r's with big R's. So my Gibbons-Hawking term is the integral of root hk over the manifold, so I need the volume form. So my root h, it's got a root 1 minus 2gm over r squared sine theta, d tau, d theta, d phi. So that's my integral. That's the sort of volume element. So I put that all together. So I guess the first thing to notice is that in this integral, tau, theta, and phi, nothing depends on tau, and the only thing that you've got which has a dependence is the sine theta d theta, but this is just giving you the area of the unit sphere. So my integral gives me a 4 pi beta, so this is sort of from the d tau, d theta, d phi integral. And then I'm just literally picking off the capital R dependence of root hk. So that, if I put it together, is 2 over r, 1 minus 2gm over r. So this is the k part. And then, of course, I've got the r squared from sort of sitting from the root h. So multiplying this out, this is what I get. So it's not 0, but unfortunately it's gone the other way, because it's linearly proportional to the cutoff radius r. So as r goes to infinity, this is blowing up. So we've gone, so it would seem, from 0 action to infinite action. So we've been a bit too enthusiastic. So what's going on? Well, if we look at this expression and set m to 0, you notice it's still divergent. So that means that flat space has a divergent action if we compute it in these spherical polar coordinates. So what that suggests, therefore, is that we need to do a background subtraction. So if flat space has a divergent action, then what we do is we simply say, OK, so if flat space time is diverging in this particular way of writing it, then that's just some intrinsic divergence that we renormalize. So we take it away. So I write flat space in polar coordinates, but notice I've put a constant in front of d tau squared because I must, if I'm going to subtract off a background action, then the two boundary manifolds have to agree. And therefore, the periodicity of the times has to be the same. So I have to have the same periodicity of Euclidean time in order to do the subtraction legitimately. And so that means, because I want a very specific periodicity here for tau, I'm going to just put in a constant to say, well, I'll choose my lambda to make sure that the manifolds match up at capital R. So if I then ask, what is the boundary? So this is our delta m naught, r equals r, again. So because in both cases, r is the areal radius, that means I put the manifold, the boundary of the manifold at the same capital R. But now, if I want to have the time components of the manifold being the same, I've got to have the circles to match, the time circles. That tells me that lambda has to be 1, lambda squared, sorry, has to be 1 minus 2gm on R. Yes?
Does this happen that you get a divergence no matter which submanifold you pick? Because you're picking the radial coordinate.
Yeah.
As a constant, the submanifold to compute the Gibbons-Hawking term.
Yeah.
What if you pick something else?
So that's a good question. So what would you imagine picking? So we have to sort of think, well, what else could we pick? So if we were in flat space, we could imagine, I suppose, taking Cartesian coordinates and having a cube or something like that. So in that case, all the faces of the cube would have zero extrinsic curvature because they're just flat. But then we'd have to worry about edge effects because we'd have edges to the cube and corners to the cube. So on the corners to the cube, we'd still have, some extrinsic curvature because we're kind of gluing together different different patches. So you could imagine taking, I suppose, two flat pieces of paper like that and then rounding off the corner. And so if you think about what that looks like, so the corner now is, let's say it's part arc of a circle or something. So we know that the cylinder, as an embedded manifold, has no Ricci curvature, but it does have extrinsic curvature. So you'd still get extrinsic curvature on the edges of the cube and at the vertices of the cube. And indeed, at the vertices, so the edges of the cube would have extrinsic but not intrinsic curvature, but if you try to smooth off the vertices, they would have both extrinsic and intrinsic curvature. So I think so I'm just thinking on my feet here, but I think even if you had a cube, you would still have some extrinsic curvature from the edges. What an excellent tutorial question, David, as a practice for extrinsic curvature. Shrugs. Okay, maybe not. So just thinking of that particular example, where you might think, aha, I can get round this because I've made flat surfaces. I think that even in that case, you'd still have some residual curvature certainly from vertices and I think from edges as well, because each edge would have an extrinsic curvature of like proportional to 1 over r, where r, or epsilon, where the epsilon was the scale of the of the cutoff. And then you'd have to integrate round that, which would give you a factor of epsilon coming from the sort of size of it. So that would still give you a finite answer. It's a good question.
So when we are using this term, boundary term, we have that freedom, right? To
choose boundaries.
Yeah.
Yeah, you certainly do. And so usually whenever you've got a freedom in gravity, you use it to make your life as simple as possible. And so in this case, because your space-time is spherically symmetric, then, the natural thing to do is to choose a boundary that reflects that symmetry, so that here our integral over the boundary coordinates, d3x, doesn't care, in a sense, where that boundary is, because you've got just the sine theta d tau d theta d phi is what gives you the 4 pi beta. And so that part of your job is very easy. If you changed your boundary so that it was moving through R, you would then have to worry about how you would now get a non-trivial prefactor in front of that sine theta d tau d theta d phi, which would then be you'd then have to think, oh, how do I handle this? What do I do with it? So, yes, I think it's a good question. I think, but I'd have to work it out, go and sort of sit there and work it out. But I think if you're, all I can say is if the action of flat space were finite, then if you you'd still have to match, actually that's where you'd have trouble, because you'd have to match, you've always got to match up the boundaries. So that's why you've got problems. You always have to match the boundary metric, because you have to say, well, I've got the same boundary and I'm either filling it in with the black hole or I'm filling it in with flat space. And if you change the radial coordinate in Schwarzschild as you move in the radial coordinate, you have a different periodicity. You have the same periodicity of tau, but a different length for your time coordinates. So you then from the perspective of flat space, I don't see how that would work, actually. So in fact, I think this is the only thing that you can do in this case. So that's not to say in other cases there wouldn't be choices, but I think this is the only one in this case. Right. So for M0, for our flat space-time, our extrinsic curvature is just 2 over r because there's no mass term. And the factor, root h0 d3x, gives 4 pi beta again. But now our root h0 is 1 minus 2 gm on r and r squared. So therefore, our integral of root h0 k0 now has this square root in it. And then we simply say, well, r is big. So I Taylor expand my square root. And I find that the integral of root hk is 4 pi beta into 2r minus 2gm. So, as we might have suspected, the linearly divergent term cancels, which it really should. But notice that this also has a piece that has gm in it, and that's because we've matched the circles at capital R. So I put everything together, and I find that my gravitational action for Schwarzschild is beta times m over 2. So that's now nice and finite, and it's dependent on, explicitly at least, on the periodicity of Euclidean time times the mass. But of course, we remember that beta was 8 pi gm. So we know that this is really 4 pi g m squared. So as I said at the beginning, I was sort of saying, you know, whenever you're doing this kind of Euclidean argument, there's always a sort of sense in which you feel maybe it's a bit dodgy. But I think the reason why we take it seriously is because so much work fits together and so much makes sense. So we have this periodicity of Euclidean time agreeing with the Hawking calculation. So we have the same temperature, even if it's a bit shady interpreting, you know, it as a thermal equilibrium. The other thing that works nicely is if we consider a partition function, so normally this might be a sort of trace of e to the minus beta h, where h would be the Hamiltonian. So that might be representable as a sort of integral over space of a Hamiltonian density. Which in our case is an integral. So if we assume that we've got fixed periodicity Euclidean time and sort of take 1 over beta and add in time to that integral, it's now integrating over our Lagrangian density. So this is essentially our Euclidean action over beta. So it tells us that our partition function is basically looking like the trace of the Euclidean minus the Euclidean action. So then the sort of standard law is that we say, okay, so this is like our path integral. It's going to be dominated by saddle points, which are classical solutions to that, the Euler-Lagrange variation of that Euclidean action. So we might say, okay, so we've got this Schwarzschild solution as some sort of saddle point. Our entropy then is given in terms of a differential of this partition function with respect to beta. So this the log of the partition function is just this Euclidean action. And m over our Euclidean action over beta is just m over 2. But of course, we know that beta is 8 pi gm, so m is beta over 8 pi g. So this just gives us beta squared over 16 pi g. And then we replace again, beta is 8 pi gm, to get 4 pi g m squared, which is 2 gm all squared over g. Now, let me see. I've got to have some pi's in there somewhere. There we go. Which is, of course, the area over 4g. So I think, I'm not saying, we're obviously not going to do partition functions in any depth, but it's simply to say that, when Gibbons and Hawking were getting their boundary term and looking and exploring whether this Euclidean approach made sense, it wasn't just the temperature that was kind of working, it was also the entropy. Mm-hmm.
When you're calculating the Hamiltonian, how did you go from the Hamiltonian density to the Lagrangian?
Well, in this case, I guess it's just saying, well, this is in terms of the Euclidean space, in terms of the GR, this is what that is. Yeah, so there's all the, yeah.
But, even if you include, the terms for the legendary transformation, this is a stationary space-time, so they
so it doesn't matter.
Like that. So really, the Hamiltonian is the Lagrangian, basically.
Yeah. I mean, there's a lot of kind of going out on a limb going on here by saying, we're in this static situation, we're in thermal equilibrium, when we know full well that the black hole isn't in thermal equilibrium. Nonetheless, there's a lot of things that seem to be fitting together, at least, within the context of saying, okay, let me forget that this thing has a back reaction on the black hole. And in fact, of course, we don't really know, we haven't really solved the problem of Hawking radiation, back reaction, and what happens, which is still a source of active debate and research. What happens to the black hole, Because you can throw all sorts of mess into it, and yet apparently you get a thermal state out. So what happens to that information when the black hole evaporates? So there's a lot of puzzles and questions over this particular boundary or this particular kind of interaction of field theory with gravity. I think when you're doing cosmological perturbation theory, people are much more comfortable about doing the usual approach of kind of meshing together field theory and gravity. They take the background manifold and then quantize all fluctuations. And that seems to work extremely well. But that's because the cosmology is somehow stable. The universe is expanding, structure forms, and everything's fine. Whereas for the black hole, it's kind of on this precipice, you know. So this is really very much a sort of still a little bit into the unknown. Right. So that's kind of the formal bit of Gibbons and Hawking. So I now wanted to go into thinking about a rather different application of Gibbons and Hawking, and actually one that predates the Gibbons-Hawking boundary term by a good decade, which is thinking about physical sources that are hypersurfaces. So why might you do that? Well, the reason that Werner Israel originally did this back in the 60s was he was trying to think about how, say, shells of dust might accrete onto stars or black holes, or just thinking about structures in cosmology or astrophysics that were essentially sheet-like. How might they look gravitationally? So I'd like to kind of access this by thinking about an example. So remember, when we did the variation of the action, I actually kept this term in because I wanted to come back to it. We got two pieces in varying the Gibbons-Hawking term. We got a piece that was telling us about the normal variation of the metric, and that we needed to cancel with the variation of the Einstein action. But we also had this second piece, which is the sort of traditional type of Euler-Lagrange boundary term that you get, something proportional to variation of the actual field, the metric, on the boundary. So what if we think of some shell in space-time? So I'm imagining something which is kind of thin compared to the scales of interest. So we could view that as being an M minus and an M plus, having two sides. And therefore, the shell itself would be like the boundary or the combination of the boundary of M minus and M plus. So if we think about this from a Gauss-Codazzi perspective and looking at the variation of the action there, so notice that our normals, so there's a sort of slight, I don't want to get I think there's an issue always with signs in the choice of normal, whether it's inward pointing or outward pointing. And in Euclidean space, it doesn't matter whether your normal is a covector or a vector, because it's still going to have the same sign. But of course, it matters in Lorentzian space. But basically, in terms of the Gibbons-Hawking expression, your manifold there, this would be n plus and n minus, but you would prefer to have the normals facing in the same direction. So to get this minus sign, you kind of flip the normal. So that the two normals align. So this gives you the Israel equations. Where you take the energy momentum tensor for this surface here is strongly localized, and you approximate, you might think it's a delta function. And so you integrate your energy momentum through the surface, and that gives you this SAB. It's just the integrated energy momentum tensor. So what you're saying is that TAB is roughly SAB delta of Z, where Z is a coordinate through the wall. Now that's actually quite loose phrasing there. If you want to do this rigorously, what you do is you set up a thin but finite thickness wall, and you set up a coordinate system in which you say the wall is centered at Z equals 0. Z is your proper distance through the wall. We essentially did this when we were setting up Gauss-Codazzi. We had n was geodesically extended, it was unit, and therefore the integral curves of n define you a Z coordinate, which is proper distance through the wall. So you would do that. You would then look at your Einstein equations and decompose them parallel, perpendicular to the wall, and then you'd gradually let the thickness of the wall go to 0. And you would find that this would be the expression that you would get in that limit. And so in GR, even though it's a nonlinear theory, you can still take a delta function of a codimension 1 surface. And essentially, that's because if you're just doing a 3 plus 1, but in the sense of a codimension 1 decomposition of your space-time, there are no sort of non-linearities because you've only got the one coordinate going normal to the wall. So this delta function is so this delta, remember when you define the delta function, or it's not really a function, it's a distribution, you do so as a limit of smooth functions, and you show that the delta function expression is independent of the way you take that limit. And so you can do the same in GR, but only for codimension 1. Doesn't work for any higher codimension. So now, that's sort of saying this is what we expect. So let's look at an example. So I want to consider this surface, x squared minus t squared is L squared, in Minkowski space-time. So to get the normal, if I look at dx squared minus t squared, that's 2x dot dx minus t dt. So this is going to be proportional to my normal. That's basically saying this is what the normal is of the surface. To make my calculation easy, I'm going to put coordinates on this hyperboloid. And I'm going to coordinatize it by tau, theta, and phi, because at a constant time, my hyperboloid is spherical. And so I just simply take a coordinate, take the theta and phi to coordinatize those spheres and allow time to run up the hyperboloid. So my surface, sigma, this is sigma, so in terms of the intrinsic coordinates, if I want to define my hyperboloid, notice that the length, this is in polars. So the x squared here is just r squared. R squared is L squared cosh squared. I subtract t squared, which is L squared sinh squared, and I get L squared. So this defines my embedding. And of course, I've got 3 coordinates because it's a hypersurface. So my normal has this form. So if I think of what tangent vectors lie in the space, so my x mu, comma, the tangent vectors, remember, are dx mu by d sigma a. So obviously dx mu by d theta has a 1 here. There's nothing there. My dx mu by d phi has a 1 there. There's nothing there. And dx by d tau, which is the final coordinate basis vector in the tangent space of sigma, is going to be cosh tau on L, sinh tau on L. So you see that n annihilates that as well. So this gives me, if I look at the theta-theta component, in terms of the higher dimensional manifold components, I've got to take the covariant derivative of n, and that's just because nr just depends on tau. That just gives me the gamma piece. Okay, so the gamma r theta theta, if I just think about the higher dimensional polars, is simply r, so that's what I've got, rnr, but of course my r coordinate is L cosh tau on L, and my radial piece of n is also cosh. So I get L cosh squared tau on L, but g theta theta is just r squared, which is L squared cosh squared. So this is just g theta theta on L. And similarly, So if I want to write my curvature in terms of its intrinsic components, then I find it's proportional. My extrinsic curvature is proportional to the intrinsic or induced metric. So if I look at that combination of KAB minus KHAB, or intrinsic metric, I get 2 over L times that intrinsic metric. So you kind of should have expected this, because remember when we talked about de Sitter space, I said you can represent de Sitter space as a hyperboloid in a Lorentzian space-time of 1 dimension higher. So I wrote down the embedding and I said, oh, the hyperboloid inherits a metric from the 5-dimensional Minkowski metric, and that metric is the de Sitter metric. And of course, de Sitter has a cosmological constant. Its energy momentum is proportional to the metric. And so what you're seeing here is, if we look at the Israel conditions, Israel is telling us that jumps in extrinsic curvature, this combination of KAB minus KHAB, are telling us about energy momentum. So here I'm getting, if I think about the extrinsic curvature of the hyperboloid, I'm getting something that looks like an energy momentum that's a cosmological constant in the hyperboloid. But of course, at the moment, all I've done is just taken the hyperboloid. If I were to just have the hyperboloid with its inside and its outside, the two expressions for the extrinsic curvature would be the same, okay? So in other words, if I say this is m plus and the outside is m minus, then k minus AB is equal to k plus AB. And so I don't get any energy momentum at all, which you would kind of expect. If I just lay down a surface in Minkowski space-time and just say, well, okay, I've got this surface that has an extrinsic curvature, but if I don't put any energy momentum there, then I don't expect to have any gravitational back reaction. And so in that sense, this is just Minkowski space-time arbitrarily split in two. So there's no energy momentum there, so I expect this. But if I take two interiors, so in other words, I take my hyperboloid, this is m plus, I take a second hyperboloid, second copy, and take the interior of that one, m minus, then my extrinsic curvatures are sort of equal and opposite. So remember that m plus has a normal kind of doing this, whereas m minus has a normal pointing out of what you're keeping. Hope I've got my maths right here.
In this case?
Oh, my indices are wandering, aren't they? Just a sec.
In this case, I don't understand what the boundary is or the surface.
So what you're doing is, at the moment, I haven't really given you a reason for why you should do this, but I'm taking two copies of the same setup where I start off by laying a hyperboloid down in Minkowski space-time. The hyperboloid, my manifold that is the bulk manifold is the interior of the hyperboloid, so that's my four-dimensional space, and its boundary is the hyperboloid. So that's m minus and the delta m minus. I now do the same thing. I make a second copy of it, of m plus and delta m plus, and then because I've now taken a mirror image, I actually have a difference, sort of the extrinsic curvatures are like equal and opposite. So if you try to stitch together, so if I gave you a cylinder, for example, and I asked you to stitch together the interior of one with the exterior of the other, you could simply slide the sort of interior inside the gap of the exterior, and then you would see everything fitted together perfectly. There's no tension anywhere. And so you could just remove that arbitrary surface because I've got the interior with the exterior. Now I've taken two interiors. So if I literally try and stitch those together, if you sort of imagined, taking a needle and thread and trying to stitch them together, you would find you would have tension, because in trying to sort of glue these bits together, you would be having to sort of pull, right? And so that intuitively is the energy momentum that's across that boundary. So this is kind of needlework, if you like, with manifolds. You're kind of stitching and gluing things together, and if you have no tension, everything can be sort of done together in a flat sense, but if you sort of have slightly different boundaries, such as like needlework, then you start to generate curvature. So like making a garment. So what we'll see next time is actually, this so far looks a bit, it's a bit cracked, isn't it? You're saying, well, why would you do that? Why would you do that? She's just trying to do something just for the sake of it, just to be awkward. But what we'll see next time is we'll look at an actual physical source which has precisely that approximate form for the energy momentum. It's highly localized, and it's just proportional to the intrinsic or induced surface metric. And if we pretended we'll forget about all this, all we'll do is just march forward and solve the Einstein equations for that particular source. And then what we will see is that what we get is precisely this, rewritten in terms of this orthogonal coordinate. So although it looks a bit bizarre, I'm just going to ask you to have a little bit of patience, and we'll see tomorrow how this does correspond to some actual physical source. So that's when we'll look at physical submanifolds and actually thinking about how you can have some non-perturbative solutions of quantum field theory within gravity in a meaningful way.